Hey everyone, welcome back. We're still on Module 3, Topic 3, Lesson 3. We have moved on to page 503. Lots of threes there. This one I hadn't recorded before, so I'm doing this on a separate video. It says, analyze each table of values, identify the independent and dependent quantities in each, then write an equation that models the relationship. Okay, so let's see. Independent and dependent. So if this is the X and this is the Y, we always say that this is the independent and this is the dependent. So the total profit made and the profit made by each person. Like, does that make sense? Does just going based on XY actually work out when I think about the scenario? So if we're talking about the profit made by each person, if there was a total profit, this amount would depend on the total. So that absolutely makes sense. So if we write an equation for that, we would say, let's do T for total profit. So the profit of each person is the dependent that goes out in the front, is determined by the total profit divided by, let's see, what would we be dividing by? It's here, you have to kind of think it through. Let's kind of write it out because there's a pattern here that occurs. So this is the total. So we're doing T for total. This is P for the profit. This is for the individuals, the individual person. So the total profit is split among some number of people. So the profit each person gets depends on the total profit. Let's see if we can figure it out. So if there's $21 profit made and each person gets $7, how many people would there have been? And does that work for the others? This one's a little bit harder to do in your head, so let's hop down here. 45 divided by 15. And we'll double check on the 2550. I'm assuming you have a number in your head already. Divided by 850. Did you have the number 3? Yep, so they're all dividing by 3. So there's 3 people splitting that profit. Okay, so boxes of cookies sold and the total profit. Okay, so we'll do T for the total profit and, oh, I don't know, let's do B for boxes. Actually, I'd better make that a lowercase b. B for boxes, T for total. So 3 boxes of cookies gives you $7.50, 5 boxes gives you $12.50, 7 boxes sold $17.50. So this total profit depends on the number of boxes sold. And this is the dependent. Again, this is our X column and this is our Y. X is always the independent. So you take the number of boxes sold. So number of boxes sold times some amount equals the total cost. So what is that amount that we would be multiplying by? Well, here's where we could figure it out as a unit rate. So 750 for 3 boxes would be what for one? So you do 750 divided by 3, it gets you 250. Does that work for all of them? You can either do 3 times 250, 5 times 250, or you could do 1250 divided by 3, and you get 5. All right, so let's just double check it. Okay, so 1250 divided by 5, yep, we get 250. And you can check with multiplication. We could do 7 times the 250, and we get 1750. Notice in the calculator, it drops off that last 0, but because we're talking about money, we know that it's actually there. Okay, so what's our equation then? So we know this is 250. So we have the number of boxes sold times 250 gives us our total. So $2.50 times the number of boxes equals our total. Or we could put total equals $2.50 times the number of boxes. You could do N for number. You can do B for boxes. It doesn't matter, your choice. If you did the N, you'd have T equals 250N. Okay, moving on. Number of tiles required and the number of tiles ordered. Now, when our table is set up horizontally instead of vertically, most generally your X is the top line and your Y is the bottom. So this should be our independent and this should be our dependent. Let's check. So the number of tiles required and the number of tiles ordered. So if there's 75 required, they're ordering 90. There's 95 required, they're ordering 110. 115 required, they're ordering 130. So I don't see a multiplicative relationship like we did here where we're multiplying. What's happening between each of these? Do you see it? So we'll have R for the required. I'm not going to tell you just yet, so hopefully you're thinking about it. And T for the total ordered. So to get that total ordered, what are they doing? They're taking that required amount and doing what to it each time? Right, they're adding 15. So this is an additive relationship. The other two are multiplicative. Okay, let's move on to page 504, activity 2. Analyzing relationships in graphs. The graph shows the relationship between the distance of a train from the station and the time in minutes since noon. So we have 1 minute since noon is 10 miles from the station. Let's see, 3 minutes since noon is 12. 5 is 14, and 8 goes with 17. Okay, so what is happening here? It's not going to be multiplicative. It's not proportional. Define variables and write an equation. So we'll have D for distance and T for time. So it looks like the total distance, what's happening between each of these? At 1 minute, past noon, they were 10 miles out. 3 minutes past noon, it was 12. 5 minutes, it was 14 miles. 8 minutes, it was 17 miles. So it seems like we're taking the time and adding 9 minutes to it. And if we were to connect the dots here, and you should, please do this. If you connect these dots, this line, if you notice, where's it cross the y-axis? Right here at 9. So that makes it make sense. At 0 minutes, at 9 miles, at 0 minutes since noon. So at noon, the train was 9 miles away. So how far is it? 20 minutes after noon. So we're just going to take our equation and put a 20 in for the time. So it is 29 miles away. Now, do all of the values on this one make sense? So remember, they both have to make sense for it to be continuous. Can you have a part of a minute? Yes. Can you have part of a mile? Yeah, so all of those quantities would make sense. Yes, both quantities are continuous. Okay, you pause as you need. I'm going to flip over here. The graph shows the relationship between the height of a plane and its distance in miles from the airport. So very similar thing. It wants us to complete the graph using the points. So we have to figure out first how this is broken up. The distance is pretty easy. So that looks like it's right on one of the numbers that's already labeled. So I can fill that out pretty quickly. We have 1, 2, 3, 4, 5 spaces between 0 and 10,000. So 10,000 divided by 5 is 2,000. So this is going up by 2,000s. So at 50, we're at a height of 2,000 feet. At 100, we're going to be at 4,000 feet. We can really even just use the numbers here. At 200 miles, we should be at double the 100, so double the 4,000. We should be at 8,000. We can check that. Yes, that's where 8,000 would be. And then 300, we should be able to add these two together. So it should be at 12,000. Let's check that. So it comes over here. It's the line right above, and that is correct. And it says write an equation to represent the relationship between the quantities. Well, let's see. So we have the distance for D and H for the height. So what is happening? Our height is determined. Remember, so this is the X, this is the Y, this is the dependent, this is independent. We want to start with our dependent variable. So the height is determined by, the height depends on now what is the relationship between these? We have to find our per unit rate so that we can do our times our distance. So if we have 2,000 feet and 50 miles, how many feet is it for 1 mile? Right, 40. Does that work for all of them? 8,000 feet and 200 miles? Yes, it does. 40 over 1. So we have 40 miles times the distance gives us our total height. What is the height of the plane at 150 miles? It says use the graph to justify your answer. So if I go up here to 150, let's see, we would need to draw our line though. So let's connect our dots because we need to see where that crosses. And at 0 miles from the airport, it's not going to have any height at all. So it looks like it's crossing right here. So that's right here. So 2,000, 4,000. So that should be 6,000. Oh, it looks like we didn't really finish our equation. Oh, yeah, we did. I thought that was a fraction bar. It's 40D, not a fraction bar. So what is the 40 representing here? So it says the graph shows the relationship between the height of a plane and its distance in miles from the airport. So where do we see the 40 at on here? Kind of right in here. Okay, so I plotted the wrong 40 here. This 40 is not what this is. So at 2,000 feet in the air, the plane is 50 miles from the airport. So if we did the per one, divide that, we have 40 feet for every mile. So every mile the plane is away from the airport, it ascends another 40 feet. So at 1 mile from the airport, it's 40 feet in the air. At 2 miles from the airport, it's 80 feet in the air. And so on. 3 miles away, it's 120 feet in the air. So this 40 feet and 1 mile would be way over in here, almost at the 0, 0. So small you can barely even see it on here. Again, not a very detailed graph, which is what makes it semi-confusing. Okay, got that straightened out though. Connect the points to show the shape of the graph. Do all the values on the line make sense? The miles and the distance in miles and the distance in height are both continuous. So yes, both quantities are continuous.